situations that may lead to problematic relation schemas and proposed informal design guidelines for a good relation schema design. So now we will learn about a formal constraint among the attributes, that is the main tool for formally measuring the appropriateness of attribute groupings or for checking the goodness of relation schemas design. Functional dependency. Functional dependencies are used to specify formal measures of the goodness of relational schema designs. Functional dependencies and keys are used to define normal forms for relations. They are constraints that are derived from the meaning and interrelationships of the data attributes. So, functional dependencies are the formal measures for checking the goodness of the relation schemas design. They are used to specify the normal forms for checking the goodness of the relations, and we can say that these are the constraints that are derived from the meaning and the interrelationships between the attributes which are grouped into the relation schema. A functional dependency is defined as a constraint between two sets of attributes in a relation from a database. The concept of functional dependency arises when one attribute is dependent on another attribute and it uniquely determines the other attribute. So functional dependency is the constraint among attributes, and it arises when one attribute set is dependent on another attribute set, and also it uniquely determines the value of that attribute. Now formally, if we define functional dependency, then we can say that if we are given a relation R, a set of attributes x and y in R, then the set of attributes x is said to functionally determine the set y in R if and only if each x value is associated with at most one y value. So this definition says that a set of attributes x functionally determines a set of attributes y if the value of x determines a unique value for y. Whether the value occurs more than once in the values of the x and y occur more than once in the relation, but whenever the value of x occurs, the value of y will not change. It will remain same, it will remain unique for the particular value of x. If given a relation schema R with state R and x and y are two sets of attributes, then functional dependency is denoted by x arrow y. It specifies a constraint that for any pair of tuples t1 and t2 in the relation state R, if t1x is equals to t2x, then t1y is also equals to t2y. This formally this is defined like this. Informally, if we say that for every value of x there is unique value of y, then we can say that x functionally determines the y. Thus, given a tuple and the values of the attributes in x, one can determine the corresponding value of the y attribute, and in simple words we can say that if value of x is known, then value of y is certainly known. For example, consider we have two sets of attributes x and y. Y is functionally dependent on x, or you can say x functionally determines y. Then this right hand side of this functional dependency is y, and left hand side of this functional dependency is x. Here x is called the determinant set that functionally determines the value of y. It refers to the attribute or group of attributes on the left hand side of the functional dependency. Y is called the dependent set. So on the left hand side, the set of attributes is the determinant set, and on the right hand side of the functional dependency is the set of attributes which is called dependent set. Functional dependency constraint versus key constraint. A key is a set of attributes that uniquely identifies an entire tuple. But on the other hand, a functional dependency allows us to express constraints that uniquely identify the values of certain attributes, not the entire tuple. So this is the main difference between a key constraint and functional dependency constraint. Key constraint is also specified on the attributes, but it uniquely identifies an entire tuple. But functional dependency is also a constraint on attributes, but it uniquely identifies values of certain attributes, not the entire tuple. However, a candidate key is always a determinant, but determinant does not need to be a key. That means left hand side of the functional dependency is candidate key is always occurs on the left hand side of the functional dependency as a determinant, but a determinant doesn't need to be a key. Thus, now we can deduce that a functional dependency is a property of the semantics or meaning of the attributes. It is a property of relation schema, not of a particular relation state. Hence, a functional dependency cannot be inferred automatically from a given relation state or extension, but it have to be defined explicitly by the database designer or someone who knows the semantics or meanings of the attributes of the relation. Relation states that satisfy the functional dependency constraints, they are called legal relation states or legal extensions of the relation. Here is an example of a relation with functional dependencies. In this, the relation is imp department. Here imp id is the primary key, and imp id is functionally determining the value of employee name, date of birth, address, department number, and department number is the foreign key of the relation, which functionally determines the value of department name and department manager id. So here we can say that for functional dependency 1, we can see this functional dependency holds means for each value of employee id there is exactly one or at most one value of date of birth, address and employee name. Similarly, for for a value particular value of department number, there is at most one value of department name and department manager id. Now we can write the function dependency 1, imp id arrow imp name, date of birth, address and d number, and d number functionally determines the set of d name and d manager id. Another example is of relation imp project. Here imp id and project number are collectively representing the primary key of the relation. So this primary key is recognizing or this functionally determining the value of the attribute r's. And functional dependency 2, here employee id functionally determines the value of employee name. In the third dependency fd3, project number determines the functionally determines the value of project name and project location. Here are the functional dependencies. Next is there are two categories of functional dependencies. One is trivial and another is non-trivial. A functional dependency x arrow y is trivial if x is superset of y or y is subset of x, otherwise it is non-trivial. For example, employee project is a relation. Here are three functional dependencies. First is employee id and project number collectively functionally determines the value of project number. Employee id and project number also collectively functionally determines the value of employee id, and also employee id and project number determines the value of r's functionally. Out of these three, first two functional dependencies are trivial, because we can see here that project number is the subset of the employee id and project number set, and employee id is also the subset of the set employee id and project number. So these two functional dependencies according to the definition are trivial functional dependencies. And last one here, ours is does not belong to the set employee ID and project number, therefore this functional dependency is not trivial. This is non-trivial functional dependency. Next are some inference rules for functional dependencies. Inference rules actually deduce the functional dependencies, more additional functional dependencies from the existing functional dependencies. Armstrong given three rules, inference rules. First one is reflexive rule. It says that if y is subset of x, then x functionally determines the y value. So reflexive rule always gives the trivial functional dependencies. Second one is augmentation rule. It says that if x functionally determines y, then x union z will functionally determine the value of y union z. That means on the left hand side and the right hand side we can append a new set of attributes, and that particular functional dependency will also hold. Third is transitive rule, which says that if x determines y and y functionally determines z, then we can infer that x functionally determines the value of z. So these three rules, A1, A2 and 3, reflexive, augmentation and transitive, they form a sound and complete set of inference rules. Some additional useful inference rules are also there. One is decomposition or projective rule. If x functionally determines the value of y union z, then we can infer that x functionally determines y as well as x functionally determines z. Union or additive rule. It says that if x functionally determines y and x functionally determines z, then x also functionally determines y union z, which is, so union or additive rule exactly opposite is exactly opposite of the decomposition or projective rule. Pseudo-transitive rule says that if x functionally determines y and w union y functionally determines z, then we can infer that wx functionally determines z. Now consider a relation imp project. Based on the rules which we have provided, which we have discussed, now we can derive or we can infer new functional dependencies like employee ID and project number collectively determines the value of project number. This functional dependency is inferred using the reflexive rule. Employee ID and project number collectively functionally determines the value of employee ID. It is also inferred using the reflexive rule. Employee ID functionally determines the value of project location. So this functional dependency is inferred or deduced using the transitive rule, because employee ID functionally determines the value of project number, and indirectly we can say that the employee ID is also determining the value of project location. So this is transitive rule. Next is closure of F. F is the set of all functional dependencies that are specified on a relation schema R, and closure of F is the set of all dependencies that include F as well as all the dependencies that can be inferred or deduced from F. So F includes all the dependencies which we have defined on the relation as well as all the dependencies that can be inferred from those functional dependencies using the inference rules. For example, consider this relation. Here two functional dependencies exist. One is functional dependency 1, employee ID determines value of employee name, date of birth, so on. Second is department number determines value of department name, department manager ID. So here value of F is the set of these two dependencies, FD1 and FD2. Now some of the additional dependencies that can be inferred from F are employee ID also determines the value of D name and D manager ID, which is a transitive which is inferred using the transitive rule. Then employee ID determines employee ID, that is the reflexive rule. department number in functional determinants department name. So if we define closure of f for the relation, we will add functional dependency 1, functional dependency 2, as well as these 3 dependencies into the set. So together these 5 dependencies represent the closure of f. So after discussing the main formal constraint that we will use to define the goodness or check the goodness of the relation schema design, now we are going to discuss about normalization, a logical design method which minimizes data redundancy and reduces design flaws. All the design flaws which we have discussed earlier, all these design flaws are removed or minimized in this process. Normalization process provides database designers with a formal framework for analyzing relation schemas based on their keys and on the functional dependencies among their attributes, and a series of normal form tests that can be carried out on individual relation schemas so that the relation database can be normalized to any desired degree. So unsatisfactory relation schemas that do not meet certain normal form tests, they are decomposed into smaller relation schemas that meet the tests and hence possess the desirable properties. So we can say that normalization is a top-down design methodology which involves evaluating each relation against the criteria for normal forms and decomposing the relations as necessary. That is why normalization process can also be considered as relational design by analysis, because here we analyze the individual relations and collectively analyze the individual relations, and after that if the desirable properties are not met, they are decomposed further into relations. So now we can define normalization formally as a process of analyzing the given relation schemas based on their functional dependencies and primary keys to achieve the desirable properties of minimizing redundancy, minimizing insertion, deletion and update anomalies, which we have discussed earlier. And third is lossless join property, a property of decomposition which ensures that no spurious tuples are generated when relations are reunited through a natural join operation. Then is dependency preservation property, which ensures that each functional dependency is represented in some individual relation resulting after decomposition. That means if before decomposition some functional dependency exists, it should also exist after the decomposition in any one of the new relations made. So this is the complete definition of normalization. Various normal forms are given by Cott. First normal form, second normal form, third normal form, Boyce-Codd normal form. So these second, third and Boyce-Codd normal form, these are based on functional dependencies. Fourth normal form is based on multi-valued dependencies. Fifth normal form is based on joint dependencies. So these are the 5 normal forms which we will discuss in the next lecture. Thank you.